Hello everyone. So let us concentrate on infrared spectroscopy in today's session. Infrared spectroscopy, as we discussed in the introductory segment of the spectroscopy techniques, we told that infrared spectroscopy is basically involved in the functional group detection in an organic molecule. So we can predict the type of functional groups present in a given organic molecule on the basis of infrared spectroscopy. Now, in a molecular perspective, if we look into infrared spectroscopy, basically deals with the vibrations present in a molecule. Okay, so vibrations. Let us quickly look into the various types of vibrations that might be present in a molecule. So to start with, let us look at the simplest diatomic molecule, like HCl. Okay, so we should always know that at room temperature, these bonds that is between a diatomic molecule, it's not like a stiff bond, that is H and Cl have a constant bond length of some Armstrong. It's not like that. This bond is kind of an equilibrium distance between these two atoms. Okay, so that means this bond is actually can be considered to a spring. Okay, so there is a constant set of stretching vibration that is happening when these molecules are at room temperature. So it's not a stiff bond, but rather this is can be considered as a spring that is vibrating constantly at room temperature. Okay, so this diatomic molecule has a stretching vibration that is present in the molecule. However, when we go from the diatomic to more complex polyatomic molecules, to simplify, let us look into a triatomic molecule. So this is a triatomic molecule. So as you can see here, we can have stretching vibration, which is on the bonds that are present in this molecule. You can have stretching vibration. Now, stretching vibration here can be of two types. One is symmetric stretching, and the another one is asymmetric stretching. Now, what do you mean by symmetric stretching? When the stretching is happening in a symmetric way. If you look at this arrow is like the CH bond is stretching in the outward direction. They are stretching together in the outward direction, or they are stretching, compressing together in the inward direction. So whatever is happening, both the bonds are either stretching together or compressing together. So that's why this type of one type of stretching that is possible is a symmetric kind of stretching. And the anti-asymmetric stretching is pretty easy to understand, because one of the bond, if it is elongating, another bond is compressing. So when this compression and elongation happen in a stretching mode, then we see that to be a asymmetric stretching vibration. So in a polyatomic molecule, it's not just a simple stretching mode is what we are observing, but we are observing two different kinds of stretching mode. One is a kind of symmetric stretching, when the bonds are elongating or compressing in the same fashion, or it could be an asymmetric stretch where the bonds are either one of the bond is compressing, the other bond is elongating. So thereby we have two different types of stretching mode possible. Now in a polyatomic molecule, since we have presence of a bond angle, because of the presence of more than one bond, there can be a bond angle between the two consecutive bonds. So this, due to the presence of this this bond angle, we can have another set of vibrations, which are basically called as the bending vibrations. So let me write that for you. Bending there is some kind of delay in the writing, probably because of some internet problem. So apart from stretching, in a polyatomic molecule, you can have bending vibrations as well. So bending can be also of several categories. One of the bending is whenever there can be an in-plane bending and out-of-plane bending. So when the bending is happening in one particular plane in a scissor kind of motion, that bending is called a scissor bending. And if it is happening in not in a scissor fashion, but they are uh, changing in the plane in same direction, then that particular bending motion is called the rocking motion. And there are two out of plane bending. That means apart from the molecular plane, if the molecule goes out of the molecular plane of the bond angle, then we say it to be of the kind of out of plane bending, which also can be of two types. One is called the twist and the other called the wagging motion. Now, all these different types of molecular vibrations you might have studied in detail in the molecular spectroscopy. So what I basically want to introduce to you in this particular video is the fact that this molecular vibrations are very important concept, and that is the basis for the infrared spectroscopy that we use in order to find out the various functional groups that are present in the molecules. So to further look into the details, the infrared spectroscopy, the infrared region in the electromagnetic spectrum belongs in this wave number, that is 4,000 to 600 centimeter inverse. Now, in the infrared spectrometer that we use for measuring these infrared spectrum, that particular instrument, we measure these uh, x-axis. So basically in infrared spectrum, we are actually plotting a graph, okay? And the graph is between the wave number in the x-axis, okay? And the percentage transmission on the y-axis, percentage transmission on the y-axis. So this figure you can see here, there is a nice spectrum given in this particular in this particular board. You can see on the y-axis we have something called the percentage transmission, and on the x-axis we have the wave number, which is written in centimeter inverse. So basically we are actually measuring out the frequency of the vibration, but since because of convenience, we convert those frequencies into wave numbers. So that is why we are representing in the spectrum, instead of the frequencies, we are writing it in the form of wave number. So infrared radiation is just the right range of frequency. So we are converting that frequency into wave number. So wave number infrared region falls in this particular wavelength range, that is 4,000 to 600 centimeter inverse. So all the vibrations that are happening in the molecule, be it a stretching vibration or be it a kind of bending vibration that is happening in a molecule, all these vibrations are coming in the in this particular infrared spectrum. So when you take a sample, okay, and subject it to this infrared radiation, what happens is that each of the bond or bond angle, they have a very characteristic vibrational frequencies. Okay, so when you subject these range of infrared radiation on that molecule, what happens is that the each bond will absorb certain frequencies in the infrared region and absorb it. Okay, so when it shows any kind of absorption, that is because that particular frequency in the infrared region is matching with the vibration of that particular bond in the molecule. So it will absorb it, and that absorbed frequency will be reflected in this particular spectrum. So if the molecule absorbs any infrared frequency, it will come as a kind of depression in the IR spectrum. So you can see various peaks. It looks like a ECG, right? If any one of you have seen an ECG, it looks similar to an ECG. Okay, so here you can see that it is a lot of spikes in the spectrum. You can see, so all these spikes correspond to the frequency that is absorbed in the infrared spectrum. Okay, so just to understand in a literal sense, let us look at this particular molecule. This is one of a ketone present, and its IR spectrum is what is recorded here. So you can see here that you have a particular peak, a broad peak that is coming here, and that correspond to your basically the OH bond that is present in this particular molecule. So OH bond has a particular frequency at which it usually vibrates. So when you subject this particular molecule to the infrared spectrum, the OH bond will absorb this particular, that is around 3400 centimeter inverse. Okay, this particular frequency, this OH bond will absorb and therefore show a peak in the infrared spectrum. Similarly, this particular functional group, that is a ketonic functional group, usually absorb in the range of 1700. So you can see there is an absorption happening at 1700, and this correspond to this particular presence of this particular functional group, that is CO. Okay, so that is why you see a characteristic absorption in this particular region. So as you can see that this infrared spectrum can be used to identify the functional groups present in a molecule. So in this particular molecule, when you look at the spectrum, it contains two functional groups. One is your OH functional group, another is your CO functional group. So using the spectrum, you can easily identify if you have a peak, a broad peak at 3400, you will say that this molecule is having hydroxy group present. And in the same way, if you have a strong band present at around 1700 centimeter inverse, we say, okay, this molecule also contain a carbonyl group. Okay, so this is the way we, like any sample, when we put it in the infrared spectroscopy, it will give a spectrum, and we will look at the peaks and its values in wave number, and then we will compare which functional group it matches with, and we predict, okay, this molecule has these functional groups. Okay, so this is the basic phenomena, how you use the infrared to actually capture the functional groups in a molecule. In the next video we will look into the two different regions in a infrared spectrum. Thank you very much for your attention.